So thank you, Paola, for this very nice introduction. And effectively, I will provide you now more a perspective from a petrologist and taking the Petit-spot volcano a little bit in a larger scale to indicate why I think, for me, it's one of the major discoveries in the last few years about intraplate volcanism on Earth. So briefly, I will come back to the discovery of Petit-spot volcano because I really like to teach to give this story for young students because it indicates that there are still some unknown on Earth to search and why it's so important to have expedition to look at this area. So in 1997, Japanese researchers have tested some submarine and found some fresh lava flow, which are basically 6 million years old. So it was unusual, unexpected to find this lava on the seafloor. And Hirano-san have calculated that regarding the age and the plate motion, that this place were basically this volcano was formed in this area. So in 2004, a new cruise go in this area and observe bumps and fresh lava flow at basically 6,000 meter depth. So this is a place where initial Petit-spot volcano was discovered. Now we have evidence from 3 sites in Japan, but we have also observed Petit-spot in Tonga, in front of Chile, in front of Thunder Arc, in front of Mariana, and also in 2 other locations in Samoa and Costa Rica, where we believe that we have some feature which are basically similar to what which are associated to Petit-spot formation. So the position of emission of the Petit-spot 600 kilometers before the subduction suggests a connection between plate flexure and the formation of this volcano. But to explain Petit-spot, we need 2 things. First, we need to have melts present at the base of the lithosphere. And then we need to have a process which allows to make brittle fracturing, allowing melts to rise up. So have we any evidence that small fraction exists at the base of the lithosphere? It's a long discussion about the existence or not of melts at this area. But the paper of Kawakatsu et al. In 2009 is for me very significant because it's really demonstrating in the same area where we have Petit-spot that we have basically melt at the base of the lithosphere. And they are able to document a very nice low velocity zone. And they are able to identify the position of lithosphere-asthenosphere boundary. And to explain this, they suggest that we have melts present in lenses to explain this seismic reduction. So I will take a few seconds to explain you why and how we could explain the presence of melt at the base of the lithosphere. And for that, I will use a pressure-temperature diagram on which I have put the volatile free peridotite solidus, and I put, in addition, for the Pacific plate, the conductive geotherm and the mantle adiabat. And you could observe that in this condition, we have no melts present. But of course, the mantle contains some volatile. And if you add the effect of volatile, and here I use the estimate for the convecting mantle from Levoyer et al., basically 200 ppm of water and 150 ppm of CO2. And I have calculated using an adapted version of Dagubsta et al. Parametrization, the amount of melt you could expect below lithosphere. And you could observe that effectively you could produce some melts, and you could calculate how much melt it's expected. And you realize that in reality, the amount of melt is extremely low, below 1%. So it's probably not sufficient to really produce a seismic reduction. And for this reason, Mark Ishman, but others, have suggested that melt is probably add to the lithosphere-asthenosphere boundary to explain the seismic reduction. So if you make this calculation and you take the melt produced between redox melting at the base of the lithosphere-asthenosphere boundary, and you add this melt in the low velocity zone, you could calculate that this addition produce significantly increase of melt proportion, and you could reach 1% of melts at least. And if you translate this in this melt in lenses, you could probably explain why we observe this strong decrease of the shear wave velocity. But this feature is not observed only in Japan, but it's also observed in New Zealand, so below the old Pacific plate, but it's also observed below younger plates in Cascade area or in Nicaragua. So this is probably a global feature. And this means, combining with the discovery of Petit-spot, that we need to rethink what we call lithosphere-asthenosphere boundary. So this is a classical view. You have the lithosphere, you have the boundary, and then you have the asthenosphere, where you could have low degree melt present. But if you now consider the thermal constraint of the stability of melt, you realize that probably first the thermal lithosphere-asthenosphere boundary is distinct from the seismic lithosphere-asthenosphere boundary. And this could be around 30 kilometers difference. And the reason is because if you look to the PT diagram, here you have melt in the asthenosphere, so you increase the amount of melt present until this point, but then you decrease this amount of melt, which could be present within the base of the lithosphere. So we reinterpret with Marco Repak this as a transition between the lithosphere, a thermal boundary layer, and the asthenosphere. And for us, the low velocity zone is this transition zone where you could have melt which had been add to the base of the lithosphere. So I think it's important also to consider that this area could change from place to place. It will depend on the amount of volatile you have in the convecting mantle, and also how the ability of melt to rise up and equilibrate within this thermal boundary layer. Now we could return to the model for the Petit-spot formation. So we have melt present here, but we need to take this melt to rise up and form the Petit-spot volcanoes. But it's not clear for me that really it's possible to develop brittle fracture until the base of the lithosphere. So with colleagues from Lausanne, we develop a 2D thermal mechanical model to constrain the rheological change at lithospheric asthenosphere boundary. And using a rheological model, we realize that the change observed below the seafloor is not associated to the change between the thermal LRB, between the change between the conductive to convective geotherm. But it's most shallower. And in particular, the viscosity change really gradually until you reach the middle of the lithosphere. And this change, which are for me the transition between ductile to elastoplastic, is associated to the change of the mechanical behavior of the plate, where we have dislocation and diffusion creep in the asthenosphere and in the base of the lithosphere, and we move after to elastoplastic behavior. But now, if you take this idea and you consider that you have melt present here, this means that first, before to be able to be extracted in brittle fracture, you need first to rise up and potentially equilibrate within the base of the lithosphere. And if you make this kind of idea, and you consider that small melt fraction cannot transport heat, as demonstrated several years before by Mackenzie, you expect that your melt will cool and could crystallize some hydrous cumulates. And I think this hydrous cumulate present in the base of the lithosphere could explain some of the characteristics of Petit-spot volcano. So in this two diagrams, the TAS diagram, and then a second diagram where we have the alkali ratio versus titanium, you could see the difference between typical OIBs in gray and petit-spot lava observed in different areas. And you could observe that, as mentioned by Paola initially, that these rocks are alkalic. But they also spend a large range of composition. But I like to use this diagram, potassium sodium versus titanium ratio, because it's allowed to distinct the potential origin of melts. Because experiment on partial melting of peridotite indicate that melt from peridotite is limited in this area. If you have garnet pyroxenite, recycling of sonic crust, you could produce some liquids which are extremely rich in titanium, but doesn't contain a lot of potassium. And to have enrichment in potassium content, you need to have hydrous phases like phlogopite or amphibole. And in this case, you could imagine that the petit-spot lavas is a mixture between phlogopite pyroxenite melt produced within the lithosphere and melt from the low velocity zone. Or in other case, you could employ hornblendite. So this constraint allowed us to suggest a slightly different model that Iran-Hossan have initially proposed. We suggest that we have melts present in the low velocity zone, but then these melts start to rise where the plate is flexure, start to rise progressively within the lithosphere. But because you have a strong geotherm, this melt will crystallize and form hydrous phases. But at some point, if you add melt and melt, you could reach a point where melts could rise to the surface and explain the mixture of composition between melts from the low velocity zone and a component which are probably related to metasomatized lithosphere. So, have we any evidence for this kind of process? I think we have three main evidence. The first evidence is coming from the heat flow measure in front of Japan. This heat flow shows strong behavior with some value which are normal, but punctually you have very anomalous heat flow. And following Yamato et al. In 2008, they suggest that this anomalous heat flow is the fact that most of the magma which produce the petit spot do not reach the surface, but produce some additional heat source within the subducting plate. The second argument is coming from multiple saturation experiments. Mashida et al. Have performed a series of experiments where they put glass coming from the petit spot and try to find the condition where this melt is in equilibrium with mantle phases, so olivine, clinopyroxene, orthopyroxene, basically. And they realized that this stability is only observed in lithospheric condition. It's below 2.5 GPa and temperature below 1300 degrees C. And the third evidence is coming from the mantle xenolites who had been carried by Petit-spot volcano. So Paola showed you a lot of very nice picture where we see Petit-spot lava containing mantle xenolites. And you have here a BSC image of xenolites containing OPX, olivine, and clinopyroxene. And it was a big surprise when we measure the composition of the CPX, because this composition doesn't correspond to what we expect for a lithospheric mantle. For a lithospheric mantle, you expect that the spectra for incompatible element here go from relatively high, moderate, heavy rare earths and decrease significantly to incompatible element. But when we measure the petit spots, the CPX from this petit spot, we realize that this composition is highly enriched in incompatible element, have a strong fractionation for heavy rare earths, indicating an equilibrium at pressure where garnet is stable. And the only liquid CPX from mantle xenolite we know with this kind of signature is coming from melt metasomatized garnet peridotite sampled by kimberlites. It's coming from Capval crater. And in this case, it's clearly liquid which have interact with the base of the cratonic lithosphere, enriches CPX. But in these rocks, we also observe normally phlogopites as additional phase. So clearly, I think the model we propose is relatively realistic. But now it's where the expedition 502 are so exciting, because experiments before this expedition, we have only lava which reached the surface. So we are very interesting to have information of the lava which has been trapped within the crust, and in particular within the sediment. So as Paola explained, we wanted to test the interaction of this lava with sediment and the potential implication for a megacrust earthquake. But as a petrologist, what I would like really to test is this kind of model. And in particular, I will show you some features which are totally unusual for petit-spot lavas. So in this expedition, Paola was and his team on the boat was able to sample in 60 meters of sediment. Unfortunately, I was not able to go to the boat, but it's something I dreamed to do one time. But below these 60 meters, we have 40 meters of lava flows. And effectively, the texture of these lava flows are incredible. It's really splendid to see this quenched crystal with dendritic growth of CPX and olivine with some phenocryst. And for me, as an experimental petrologist, I think this is typical, a natural experiment which has been performed in natural conditions. So I expect to be able to recover exactly the condition of this crystallization and better constrain what is the composition of melt rising and what is the liquid line of descent we could expect for these lavas. Now, in terms of composition, here is a diagram, total alkali versus silica, and you have the composition of dredge petit-spot lavas. So a large range of composition in terms of from basanites to alkali basalt, and also a large range in Mg numbers, suggesting that the rocks have different degree of differentiation. Now, here is the composition of the lava which has been drilled in expedition 502. This composition is at the end of the composition range we observe in this task diagram. But if you observe this composition as function the Mg number, this is a richer one in silica that's been observed. So how we could explain this range of composition? Is it a change of volatile content at depth, CO2 versus water? We could explain this range. Or is it lithology difference? Or is it the mechanism of reaction between melts rising to the surface? We doesn't know yet. But this is a very interesting question. And the other question which puzzles me is the fact that practically no rocks have a composition which are in equilibrium with mantle olivines. So this means that most of these rocks suffer a differentiation. But in the same time, many of these rocks contain deep mantle xenolites. So these have some fundamental implication for the differentiation process, because when you consider interplate settings like La Palma, we assume that most of the differentiation happened close to the top of the lithosphere or within the base of the crust. But in case of the petit-spot settings, I think we need to reconsider the fact that some differentiation could start already at the base of the lithosphere in order to be able to produce slightly differentiated magma containing deep xenolites. So this brings me to the last aspect of my talk, is the importance of melt in the low velocity zone for intraplate volcanism. I think currently we have most geophysicians believe that melt present in the low velocity zone is present basically everywhere. So we need to consider that potentially this melt could be a source of magma to interplate volcanoes. And we recently published a paper on the origin of Mount Etna, where we interpret this volcano as a leaking pipe of magma from the low velocity zone. And I think it's possible in some circumstance that we produce a huge volcano by extracting melt from the low velocity zone. And I briefly explain you what is our interpretation. We start with the presence of melt under the north margin of Africa, subducting below Sicilian block. During the initial subduction, we have a context which are basically exactly the same context of Petit-spot. We have extension, and we have some lava flow producing Iblean plateau lavas, which are tiny volume. But around 0.5 million years, we have the subduction which are blocked in this area. And we start to have a slab breakoff and the development of structural fault system. And if you compare the geometry of this subduction zone with the potential presence of melt at the base of the lithosphere, Etna is just at the right place. So we assume that melt could initially start to rise up within the lithosphere, produce the initial lava we observed at the surface, and then now, when the system develop, we are able to bring a lot of material coming from the low velocity zone to the surface. So, suggesting that melt present at the base of the lithosphere, and I think this could be present within the oceanic lithosphere, but potentially also within the continental lithosphere if this lithosphere is thinning. And this provides a new origin for intraplate volcanoes. So with this, I will thank you for your attention. I will be happy to answer to your question. Thank you.